All right, today we are going to go under the hood of artificial intelligence. I mean, we're not just going to talk about what AI does, we're digging into how it's actually built from the ground up. We're talking about the blueprint, the very architecture that lets a machine see, think, and act in our world.
So let's take a self-driving car. I mean, we see them around, and it feels like straight up magic, right? But how does it actually process this insane flood of information? Other cars, people, stop signs, and then make a split-second choice to turn or brake or speed up? Well, the answer isn't magic. It's all about architecture.
And that architecture, it all starts with what is probably the single most important idea in all of AI, the intelligent agent. It sounds kind of technical, but at its heart, an agent is just anything that can see its environment and then do something in that environment to reach a goal. This is the foundation for, well, everything, from your smart thermostat at home all the way up to that self-driving car we were just talking about. And really, at its very core, every single one of these agents runs on a super simple continuous loop. First, it perceives the world. Then it thinks about what it should do. And finally, it acts. And this isn't a one-and-done thing. Oh no, it's this constant, never-ending rhythm that powers all AI. Perceive, think, act. And then do it all over again.
Okay, so how do we actually build one of these things? Let's break it down into its most basic parts. And honestly, the best way to think about it is like anatomy. You've got the body that interacts with the world, and you've got the brain that makes all the decisions.
Now, there's a really great tool engineers use to map all this out. It's called the P's model. Let's use it on our self-driving car to see how it works. P is for performance. What does success look like? Well, for a car, it's about being safe, fast, and comfortable. E is the environment. What world is it in? Roads, traffic, pedestrians, the whole shebang. A is for actuators. These are its muscles: the steering, the brakes, the accelerator. And finally, S is for sensors. It senses. So we're talking cameras, GPS, sonar, everything it uses to see the world.
So, step one in that loop always starts with the sensors. These are the agent's connection to the outside world, kind of like our own senses. They can be really obvious things, like the cameras on a robot, or even something as simple as the text box on a chatbot. But no matter what they are, they all do the exact same job. Just gather raw data from the environment.
Okay, so all that raw data from the sensors, it gets fed straight into the agent program. This is the brain we were talking about. It's all software. Its entire purpose in life is to take those inputs, which, by the way, we call percepts, and map them to an output. It decides what to do next. It's the code that turns seeing into doing. And that decision then gets sent out to the actuators. These are the muscles of the agent. They're the parts that actually make a change in the real world. For a car, it's the motors that physically turn the wheel. For a virtual assistant like Siri or Alexa, it's the speaker that makes a voice. This is where the thinking becomes an action. So, okay, we've got the basic anatomy down, right? Sensors, a program, and actuators. But now this is where things get really, really interesting. See, the actual intelligence of an agent, it's all determined by its brain, that agent program. And by upgrading that program, we can get some wildly sophisticated behaviors. Because let me tell you, not all AI brains are created equal. The best way to picture it is like a ladder, an evolutionary ladder for AI intelligence. We're going to start with the absolute simplest type of agent, and then at each rung up the ladder, we're going to add a brand new critical capability. We'll go from pure, simple instinct to adding memory, then adding some foresight, and finally topping it off with a kind of rational thinking. Right at the bottom of that ladder, we've got this simple reflex agent. This thing is pure instinct. It just follows simple if-then rules. If you see brake lights, then hit the brakes. Super simple. But here's its fatal flaw. It has zero memory. And that can lead to some really dumb behavior, like a robot vacuum cleaner just bouncing between the same two walls over and over again because it can't remember it was just there a second ago. So to fix that whole no memory problem, we take a step up the ladder to the model-based agent. This agent actually keeps an internal model of the world. It tracks things even when it can't see them anymore. So now our little robot vacuum can actually map out the room. Big improvement. But it's still just reacting to what's happening right now. It doesn't have any concept of the future, no long-term goals it's trying to achieve. All right, the next upgrade is a big one. It gives the agent foresight. We're talking about the goal-based agent. This agent doesn't just react. It actually has a destination in mind, a goal. It can use things like planning algorithms to figure out a whole sequence of actions to get somewhere. But, and this is a big but, for this agent, any path that gets to the goal is seen as equally good. It literally can't tell the difference between a fast, safe highway route and some slow, dangerous, winding back road. And this quote here really just nails the problem. Goals are just a simple yes or no, a crude binary, you know? You're either happy because you reached the goal, or you're unhappy because you didn't. That's just not good enough for the real world, is it? I mean, there are tons of ways to succeed, and some of them are obviously way, way better than others.
Which brings us to the very top of our ladder, the utility-based agent. Now, this is the agent that can make smart trade-offs. It uses something called a utility function, which is basically just a scoring system for how good or happy an outcome is. So now our self-driving car can weigh speed against safety, or the shortest route against better fuel economy. It doesn't just look for a happy state, it looks for the best possible state. This is what makes it truly rational.
Okay, so why have we gone on this whole deep dive into agent architecture? Why does any of this matter? Because this progression we just walked through, from simple reflex all the way up to complex utility, it's not just some abstract theory. It is the fundamental blueprint for pretty much every real-world AI application that is changing our lives right now. Seriously, once you know what to look for, you start seeing this agent structure absolutely everywhere. An AI that helps with a medical diagnosis? That's an agent, perceiving patient data and recommending an action. An algorithm managing a stock portfolio? That's a utility-based agent, constantly weighing risk and reward. This framework is what powers everything from the chatbot you talk to for customer service to the advanced robots on a factory floor. So when you boil it all down, it really just comes back to these four types: simple reflex, model-based, goal-based, and utility-based. These four agent programs, just built by layering on memory, then goals, then rationality onto a simple little loop, they are the fundamental building blocks for nearly every intelligent system we have today. It's kind of incredible when you think about it. And that leaves us with a final and pretty crucial question to think about. As we get better and better at building these powerful, rational, utility-based agents that are incredibly good at maximizing their own happiness function, how do we make absolutely sure that what makes them happy is what's actually best for us? That single question, that's the challenge that's going to define the entire future of AI.